All right, let's jump in. So last time we went over the syllabus. If there's a few people that have come in to the course late, so that's all on Blackboard. Um, you can check out the YouTube playlist too, where all of the lecture videos are going to go. There's like a couple of years ago, the lecture series is on Blackboard too, so they're pretty much the same. But if you want the latest one that I recorded in front of you guys, then that's the one that's on YouTube. That's okay. And so today we're going to really get started in talking about the things that science ran into that they couldn't explain. So the failures of classical physics. And then we're going to explore how quantum mechanics answered those questions. And so it opened up a whole new area of science. And spectroscopy was the tool for that. So this course is a quantum mechanics and spectroscopy course. Spectroscopy is the application of quantum mechanics. Quantum mechanics was developed to explain spectroscopy. And my goal here is not necessarily to turn you into quantum physicists, okay? Now, some of you guys may be very interested in that and go on to grad school and work in that area, but we have a lot of forensic chemistry majors, and so you're going to be going into the practical side of spectroscopy. But what I would like for you to do is to understand the theory underneath the spectroscopy, so that when you're in the workplace and a new spectroscopic technique comes along, you'll understand the theory, because all of them are based on quantized energy levels. And so if you understand a little bit about quantum mechanics, then there won't be a new spectroscopic theory or spectroscopic method that comes along that you can't understand. And so that's the goal of this course and the goal of this lecture, to kind of give you the history of quantum modes of thought. So you know these names like Einstein. You maybe have heard of Schrodinger. Anybody heard of Schrodinger's cat? Okay, and the jokes about that and so on. And Planck's law or Planck's constant, Boltzmann's constant. These were scientists in 1700s. Boltzmann was 1700s. Planck more recently in the 1900s. Before all of these, even before Newton, we had a philosopher, Rene Descartes. Anybody heard of Descartes? You've heard of the Cartesian coordinate system? That's coming from his name. Okay. And so he was a philosopher back in the 1600s. Philosophy was part of branch of philosophy. Natural philosophy was studying nature. And so they were trying to figure out what is it about nature that we can understand. And he wrote a book called Rules for the Direction of the Mind. And his rule number 4, this seems very basic to us, because these philosophers really created the water that we swim in. So it seems weird to sort of think about the day when you didn't really have a guide for truth. Now we really know mathematics is a great way to find out what's true. Collect data, make a hypothesis, test the two, and those kinds of things. The scientific method, that didn't exist before Descartes and these folks. So he's writing the rules for his own mind. Like, if I think about thinking, what is it that I could come up with that would give me a path through this forest? Okay, and one of them was this idea that there needs to be a method for finding out the truth. And he says, because the human mind has bright ideas, is a way to think of it, and he calls them germs of useful modes of thought. And so I sort of latched onto that and treated this kind of like a contagious disease. These germs of useful modes of thought went from scientist to scientist. And so Descartes said that mathematics is a good way of finding out the truth. And so he wrote a book on geometry. So he's looking around at the symmetry of things in nature. I mean, why is it that some flowers have 5 petals, other flowers have 7, some have 3 leaf clovers. A deformed one that has 4 leaves is supposed to be lucky, but that's not part of this. So he's looking at the symmetry around him, and he wrote this book on geometry. And it was his book on geometry that inspired Isaac Newton. So we know about Newton. We took a whole course in Newtonian physics, and pendulums, cannonballs, springs, all of those different things that we learned were all Newtonian physics. Newton's physics was so good. In fact, it allowed us to predict the future. Because what do you get when you shoot a cannon? Okay, you have a certain angle, you have a certain mass, you have a certain force, and it goes a certain distance and lands in a spot. And it hasn't gone there yet, so you're predicting the future. You're predicting where that's going to go. Okay, it was very successful. In fact, it was so successful that this germ of useful mode of thought, this math, jumped from Descartes to Newton, and it was so successful that a British poet was wanting to sing Newton's praises. Okay, now what's the highest praise you could give them? Is sort of make them equal to God, right? Now in Genesis 1, God says, "Let there be light," right? The creation of light by the spoken word of God. And so Alexander Pope says, "Nature and nature's laws lay hid in night, and God said, 'Let Newton be,' and all was light." Like he's saying Newton can't be overpraised because it's so amazing of what he's done in terms of explaining nature to us. So then these germs of useful modes of thought were caught by other scientists. So Descartes passed math on to Newton, Newton passed math on to Boltzmann, and Boltzmann really is the father of quantum mechanics. A lot of people will say that Planck is, but Planck used Newton's math. So Planck used Boltzmann's math. So Boltzmann was studying the velocity of gases at equilibrium, and he didn't have Excel, but what he did was essentially use Excel. So what do we do when we plot a function in Excel? It's not continuous. We have certain rows, like we have an increment. Like if we do 0, 1, 2, 3, then your increment is 1. And so you're plotting discrete points. And if you plot enough of them, it looks like a smooth curve, right? And so in order to make the math easier, he says, I'm not saying nature is discrete, but I'm going to use a discrete, basically table-based method to analyze the data. And he even admitted this is just a mathematical simplification. I'm not saying that nature is quantized. Okay. But Max Planck solved the blackbody radiation problem using quantized math. And he said, I don't like it because it looks like nature's quantized, but that's weird. That doesn't make sense. But it turns out that he was right. Okay. And then this math was passed to Heisenberg and then to Louis de Broglie. Okay. And de Broglie was the first one to introduce waves. And we'll look at that in a minute. And then that idea, that germ of useful thought, now we went from math to the math of waves. It's still math, but he's using waves now. And he passed this idea. He wrote it in his thesis, which is really cool. He wasn't even a renowned scientist yet. He's a graduate student writing his thesis, and he proposes this idea to use waves. And then that idea of waves gets picked up by Einstein and handed off to Schrodinger. And so Einstein says to Schrodinger, hey, check this out. This might be a useful way to analyze the data. And so then Schrodinger develops the wave theory of quantum mechanics, and then Paul Dirac turns it into a bigger, better deal. So let's go through these things. So Planck's quantized distribution was trying to solve the blackbody radiation curve. So this is the radiation that comes off of a hot object. And it's called a black body because the identity of the substance doesn't matter. And that's a weird thing too for you to consider. So whether it's copper or iron or wood or concrete, it doesn't matter. The light that comes off of it is just a function of temperature. So most of the light that comes off is infrared, but if it's hot enough, it starts to glow orange, and then a little bit brighter, it's a little white, like white light, and maybe even starts to turn a little blue as it gets even hotter. So that's black body radiation, hot body emission. Now, Rayleigh and Jeans were a couple of scientists that matched the data in the infrared. And so when they produced this curve that goes through those data points, they came up with the Rayleigh-Jeans law right here. But the problem is this wavelength in the denominator, when it goes to short wavelength, it goes to infinity. Now that's a problem because if your object is predicted as emitting an infinite amount of light, where's it getting that energy? How could you emit an infinite amount of energy? You couldn't. And if you do the experiment and you measure the light coming off, it turns around and goes back to zero. And the only way to get it to go from infinity to zero was to incorporate Boltzmann's distribution. So that's this piece right here. This is the Boltzmann piece that Planck put in. So Planck used Boltzmann's idea of discrete energies right there. And you see that H, that's Planck's constant. And he said that's sort of his increment in his Excel table. Even though he didn't have Excel, he did a table-based idea of discrete energy levels. And he said, if these are quantized by this elementary quantum of action, then the data will turn back around and go to zero. And he solved the problem. So this is our black body emitter. This is also the source of our infrared cameras and so on. Every object emits light based upon its temperature. And so when you're using night vision camera or thermal cameras, you're looking at the infrared light coming off of all objects, and everything is giving off a different amount of energy because it's a different temperature. Especially as the sun goes down, things cool off at different rates. And so it gets even better later in the night. We have a little thermal camera that we run around with looking for rabbits and stuff at night when we're out at the farm, and it's great. So right after the sun goes down, everything's kind of it's you can tell the trees and grass, and you can see animals, they glow pretty good. But as it gets darker, longer into the night, then all of the trees are different temperatures. The rocks and stuff, they all cool off at different rates, and you can look in the infrared and you can find, we've found little mice that big, driving on the gator or the mule, those kinds of little vehicles are cruising through the trails, and I'll say, stop, and we'll look, and there'll be a tiny little mouse there. We'll shine our flashlight on it, and he's just hunkered down. So it's pretty fun. So physicists thought they understood black body radiation. They had done Wien's law, which gives you the relationship with temperature, and the Rayleigh-Jeans law. But when it went to short wavelength, it went to infinity. And if your theory goes to infinity and the data goes to zero, that's a catastrophe. So this is called the UV catastrophe. And so Planck struggled with this for 6 years. So that's the one thing that I think is unrealistic about your education, is everything is in semester chunks. Okay. So you haven't struggled with a problem for 6 years. Okay. Not a math problem. Maybe you have other problems, but you haven't struggled with a math problem for 6 years like Planck did. And he knew that Boltzmann would solve it, but he just didn't like the idea of sort of claiming that nature was quantized. Okay. This work was being done with all kinds of scientists. This is the first Solvay conference in 1911. This fellow, Ernest Solvay, was a rich philanthropist, had a big estate, and he liked physics. He wasn't a physicist. He was like a entrepreneur, I guess, and he would just bring these physicists to his estate and have them share ideas. It's like the first science conferences. We didn't have the Marriott with the hotel ballroom where you could go give your scientific conference. This was what they had. And so you see some famous names. Maybe you know some of these. Well, we've talked about Planck. Here's Max Planck here, young fellow. Here's de Broglie, who we're going to talk about in a second. Let's see. We talked about the Rayleigh-Jeans law. Here's Jeans. Okay. Here's Ernest Rutherford. He is the discoverer of the nucleus. And here's Einstein. Look how dark his hair is. A young fellow there. Yeah. Here's Wien. He's the one that connected it to temperature. So the Rayleigh-Jeans law and then the Wien's law. Who's this guy with the monocle? 6. Oh, Nernst. In freshman chemistry, you had the Nernst equation for batteries. That's Nernst. Okay. And then here's Marie Curie. She's an incredible mathematician. Everybody knows her work in radioactivity, but she was a great mathematician. So she's there participating in all of it. So then we have the photoelectric experiments. So they would shine light on metals in a vacuum, and they would detect electrons coming off. And they could send those electrons through a magnetic field and see how fast they turn. In the late 1800s, J.J. Thomson discovered the mass to charge ratio of the electron. And so if you could measure the magnetic field and see how fast the electron turns in a magnetic field, you could get its velocity. Okay, and so that would allow us to measure the kinetic energy of an electron. So if we put a piece of metal here, we shine light on it, it spits out photoelectrons. So the light turns into electrons. We run those electrons through a magnetic field and measure the angle of turn. Okay, we can get the kinetic energy of the electron. And this is what we see. We see that the kinetic energy of the photoelectrons is just like a linear function with the frequency of light. So if we double the frequency of light hitting the metal, the electron comes out with twice the speed. Okay, it's twice the kinetic energy. It's actually mv squared, but if we measure the kinetic energy, it comes out with twice the kinetic energy. So we come up with this equation that the change in energy is related to the velocity, and the slope of that line is Planck's constant. Totally unrelated to the blackbody radiator. So his constant pops up in the photoelectric effect. And this is what everybody like confirmed, that Planck's constant was real. That it wasn't just a mathematical trick like Boltzmann did to solve the gas velocities. It was actually a fundamental constant of nature. So this really solidified that Planck's constant was important. Also, it was interesting that the kinetic energy did not depend upon the intensity of light. The intensity of light just gave you more electrons, but it didn't give you more energy. So we typically think of the intensity of light giving us energy, but energy is related to the frequency of light. The number of photons coming out, which we haven't used that word yet, but this idea that light is hitting the surface, if we think of it as a particle, we call that particle a photon. So these photons hit the surface and electrons come out. And those photons have a particular energy that's governed by their frequency. The intensity of light is the number of photons and the number of electrons you get out of it. Okay? There is a frequency, depending upon each metal, below which you don't get any electrons. So it seems like there's a threshold. So you shine infrared light on a metal surface, you don't get any electrons. You start to move towards the visible, all of a sudden you start to get electrons. So that's what we see in terms of frequency. So we call this the work function. It takes some work to get those electrons out of the surface. Now you guys are familiar, because you're chemists, of orbitals. Okay, you have 1s orbitals, 2s orbitals, 2p orbitals, and all of that. Okay, and so this work function is related to how deep those electrons are, how close they are to the nucleus. But they didn't know about the nucleus at this point. They didn't know about orbitals, so they just called it a work function. You have to pull those electrons out of the metal to the ionization limit, and then anything more than that will be in kinetic energy of the electron. So this is essentially what I've said. Okay, we describe that stream of particles as photons. Okay. Let's look at this from an energy perspective. Like I said, with the orbitals, we can look at those as energy levels. Okay, so this also supports this idea that light's not a wave. Think of how weird that would be if light was a wave and yet you got a single electron come out. So instead of photons, you've got a wave of light that comes in, and then all of a sudden that whole wave of light collapses and an electron comes shooting out. I always like to think about, because I like the coast, you get my boogie board and I'm going along and the whole wave disappears and I shoot off into the air. How is my little body going to absorb the energy across this whole wave front? So that's a little weird. How does a wave all get absorbed into one particle? So the wave particle thing is a little tricky in this experiment. This experiment is better understood with particles, a particle view of light. This is the basis of the photomultiplier tube. So we talked about tangible and intangible things last time. The photomultiplier tube turns these intangible waves into tangible experimental data like current or voltage. So the light comes and hits a cathode here and spits out electrons. Now we can put these cathodes in a cascading manner, and this is the photomultiplier tube. So what we have is this is the detector on all our visible spectrometers and UV spectrometers, is a photon of light comes in, hits the first photocathode, and kicks off an electron. Okay, that's the photoelectric effect. But we've got all of these charged up, very, very negative. So there's lots of electrons ready to get out of town because it's, like charges hate each other. So all these negative electrons are jammed onto this cathode. So as soon as an electron hits, it disrupts it and a bunch of them fall off and shoot over to the next one because it's a little bit more positive. So the most negative one is up here at the top. This is a little less negative. Once those electrons come off, they're going away from the more negative one to a less negative spot. And so they're constantly cascading down. As it gets less and less negative, they're attracted to the next diode. And you can see that the multiplication effect, eventually we kick off maybe 1 billion electrons for every photon of light. So this is a great way to amplify our signal. So that's the photomultiplier tube. So let's think about this work function. So if this is a metal, and up here this is the ionization limit to make a cation, our light doesn't have enough energy to make the cation. So no electrons come out. So this is what they were calling the work function. The work function was this phi. But I just call it the ionization limit now that we know about ionization and we know about orbitals and so on and energy levels. So low energy light's not sufficient to eject an electron from the surface of the metal. The amplitude doesn't affect it at all. Okay, you can turn up the brightness of the light, but if you don't change the frequency, you're never going to overcome that work function. You're not going to ionize this substance. Only the energy or frequency matters. And so this is the Planck equation, equals h nu. And then where's wavelength? Well, what's nu? C over lambda. So whenever I see you on the sidewalk out there, I'm going to ask you what's new, and your answer is C over lambda. Okay. So let's practice. What's new? C. Perfect. Okay. When we do the senior picture, and y'all are all up on the stairs and everything, I always yell it out. What's new? C over lambda. Very good. So something to look forward to. We talk about wave numbers as well, a lot in this class. And so that's just 1 over the wavelength. And it's typically in inverse centimeters. So, and you can kind of think of it as a way of saying in 1 centimeter, how many waves are there? So if there's 1, 2, 3, 4, so that's 4 waves per centimeter. But just like we don't typically say in hertz, we have cycles per second. If you look at the units of hertz, it's just per second. Here we have 4 waves per centimeter, but we just don't say the term waves. We just use the inverse centimeter. So wave number is the number of waves you have in a centimeter. If you multiply wave numbers times speed of light, then you get the frequency. Okay, what if we have enough energy to ionize the substance? So here we have the metal, and we have the cation. And our light has much more energy than the ionization limit. And so all of that extra energy comes out as kinetic energy of the electron. So the electron is ejected, and the energy is conserved. First law of thermodynamics, energy is neither created nor destroyed. So we took up some energy by getting the electron to the ionization limit, and then the excess energy comes out as kinetic energy. And so this is the technique we call X-ray photoelectron spectroscopy, XPS. This is also the energy dispersive X-ray or wavelength dispersive X-ray that we see on scanning electron microscopes. So in forensic labs, when you have a SEM microscope, you may have an X-ray detector on there. And so you can blast it with electrons, and it knocks out a core electron, another electron drops in, and then you get an X-ray out. So it's similar to this. It's not exactly the same, but we're again connecting those X-rays to the electrons in the substance, and we can use that to identify the materials. Okay, but this is all using a particle view of light. What about waves? Well, 100 years earlier, Thomas Young had used the wave theory of light to very elegantly explain the diffraction experiment. So this is Young's diffraction experiment, and he's saying if you have a light source and you run it through two slits, you get this diffraction pattern. You see the light and dark spots here? You might expect to just see two light spots because you have the light going through two slits. How come you don't just see two bright spots on the screen? You get a diffraction pattern because light is a wave. So he's saying, hey, this is evidence that light is behaving like a wave, that it oscillates. And it was not well received because it contradicted Newton. And we already said they put Newton up there with God. So this group of scientists said his work was destitute of every species of merit, which is just a very elegant way to say is worthless. It's like, great, you did this talk, but we think it's worthless because light cannot be a wave. Newton says it's a particle. And we have photoelectron spectroscopy. Well, we will. They didn't have it at that time, but they were saying Newton clearly showed that light is a particle. So, poor Thomas Young. He was right, and I don't think he ever knew that, he's now revered. The fifth Solvay conference in 27 has some new faces. Okay, here's Schrodinger, which you guys have heard of. Wolfgang Pauli, do you remember the Pauli exclusion principle? When you're putting the Aufbau, you're putting the electrons together, and you can't have, you have spin paired electrons, but you can't have a third one in there. And so that's Pauli. Here's Heisenberg. You may have heard of Heisenberg's uncertainty principle, as he solved the essentially Schrodinger's equations a different way using matrix math. Debye, I don't know if you know him, but the dipole moment has the units of Debye, and so that's him. Here's C6, Bragg. Bragg diffraction, you'll learn that in instrumental. So with monochrometers, we have diffraction gratings and so on. So that's the math related to dispersion of light, sort of the rainbow effect of thin films, is done by Bragg. Here's Dirac, Paul Maurice Dirac. Here's 8. Here's De Broglie. He looks a little older now. Okay, Born-Oppenheimer approximation. It says that the nuclei and the electrons are separable mathematically, and we'll use that later on in the course. So here's Born, and here's Niels Bohr, who came up with the planetary model of the atom, sort of like a solar system with the electrons orbiting the nucleus. It's not correct, but it was a nice first model. Okay, so good job, Bohr. Here's Max Planck. He just doesn't, I guess, these pictures back in the day were, they were slow photographs, and so they had to not move. And so I think that's why they all look so mad. It's like, don't move. And but yeah, they look ticked off. Look at Marie. She's just not very happy. Neither is Planck. Okay, here's Einstein. He's got gray hair now, and is starting to get a little wild. We've seen him in his pictures. So these conferences, it would have been great to be a fly on the wall, just to see all the debates. Yeah. So not pictured, which is surprising, he's not in here, is Bunsen. How many people have heard of Bunsen? Yeah, so you get a little burner in the lab, Bunsen burner, okay? It's kind of sad. He invented the spectrometer, okay? But instead of using a high voltage power supply, he had his Bunsen burner here. And so that's what he got his name on. The Bunsen burner is named after him, but it was the source for his spectrometer, which just seems kind of strange. It's like you invented the automobile, but they named the key after you. But the automobile is way cooler. But yeah, we got the Williams thing. Put in your Williams and turn it on. No. So this is the spectrometer, and look how they set it up. So you've got your source. Let's pretend it's the Bunsen burner. Did y'all ever do the flame test for salts? Yeah. Okay, so you put a little bit of liquid containing one of the alkali metals like rubidium or something like that, in here, and you've got a little liquid film. You stick it in, and you get a colored flame. Okay, so this is emitting light, and so if you run that, so this is the light that comes out of it. You run that through a slit here, just to give a narrow band of light. You run that through a prism, some sort of dispersing element, and you get the emission right here. And they didn't have photomultiplier tubes or diode arrays back then. They only had photographic film. So they had this film, it was all in a dark box, and so this was the data. Because the slit was like a vertical line, the data came out as vertical lines on the film. So this is what the data looked like. And you had these things called spectral lines right here. See if I can rub this out. We still use that terminology. I'm taking a little bit of a pause here to emphasize this. So the terminology we use is a spectral line, but we don't use photographic film anymore. And our slits are, maybe they're still linear, but not necessarily. And what we see are peaks. So as you come along, we have much higher resolution, and we can actually see this spectral line grow in like that. So it's the same as a peak. Same as a peak. So in a spectrum, when we see a peak in the spectrum, what is a peak shape? That's a spectral line. And so that's a very important term for this course. So when you hear me talk about energy levels and spectral lines, the lines are different than levels. So really hammer that home, because the spectral line is always a difference between two energy levels. So light has either been absorbed or emitted, and that gives us a spectral line. Okay. So atomic emission and spectra are quantized. This was another piece that classical physics could not solve. So here's the emission spectrum of hydrogen. We talked about the emission spectrum of a black body, and it was a continuum. So it would be, some long emission like that, and it would give all wavelengths of light. This is a black body curve. And the black body curve was a function of temperature. So it would slide up or down. If it got hotter, it would go towards the blue part of the spectrum. If it got cooler, it would go towards the red. All we see in hydrogen is these discrete lines. They don't really change with temperature or anything. They just have their position. And it's, there's no light here. And there's no way to get hydrogen to emit right there. It emits here and here and here. These are discrete spectral lines, and physics couldn't explain this. So this was a problem. And it was a function of different elements too. If you had iron, this is what it looked like. So very complex for iron, very simple for hydrogen. Can we explain that? Yes, this is in the electron region of the spectrum. And look at iron, how many electrons it's got. 25 electrons, hydrogen has 1. Okay, and so we knew that these spectral lines were a function of the different elements, but we couldn't explain why the lines were discrete, why they didn't really move around with temperature or anything else, and why they were lines here and here and nothing in between. Okay. So Newtonian physics couldn't explain this, and this led to the concept of electron orbitals. So these were problems with the atomic world. This black body radiation curve, it led to this proposal that nature is quantized. The photoelectric effect had this funny work function. It also described the difference between intensity and frequency. And the frequency function confirmed Planck's constant. Okay. And then this atomic and molecular spectra was still a problem that we couldn't solve, even after all of the black body things. We thought it was related to quantized energy because we have discrete spectral lines that come out of our materials. So how could we have an electron around a nucleus? We know about the nucleus now because of Rutherford. We know about the electron because Millikan's experiments and J.J. Thomson. So we kind of know the structure of the atom, but why does it have discrete energy levels? Why can't the electron be at any energy? So the atom cannot be like a tetherball where the electron just orbits around the nucleus. How many people have played tetherball? You've seen it maybe. It's a ball on a string tied to a pole, and the energy of that ball is related to the angle at which it's spinning on that string. If I pull the ball here and hit it, what's going to happen? It's going to spin around, but it's eventually going to get lower and lower and lower and lower until it stops against the pole. So it's going to have any angle there. It can have any energy within limits, right? But it can have any energy between straight out and down. Why can the electron not have that kind of energy? Well, for one thing, the electron's charged. So if I put an electron on a circular path, it becomes an antenna and it emits light. Because if you accelerate a charge, it emits light, okay? And so if it's emitting light, it's losing energy. And so it's going to slow down and get sucked into the nucleus. So what keeps the electron out of the nucleus? That's the question. And I'm sure you don't know the answer, right? I mean, what is it that keeps the electron out of the nucleus? If you're thinking of a particle, it can't stay out of the nucleus. Okay. So this is where, now they thought about orbitals as, orbits. This was the Bohr atomic orbital, and Rydberg did some experiments to show that there was a distance from the nucleus. If an electron is in what we call a 1s orbital and light comes in, it can be pulled further away from the nucleus, which takes energy, so that light can be absorbed, push the electron further out. If the electron drops back down closer to the nucleus, it could spit that light back out, and that's emission. Okay. But what would give these electrons these discrete orbits? It can't be a circular orbit. Otherwise, like the tetherball, it would shrink down and get sucked into the nucleus. So this was the issue that de Broglie was struggling with in his thesis. He liked violins. He liked classical music. And he thought, a violin string has a boundary condition, and you can pluck that string, and if it vibrates like this first energy level, it's a standing wave, okay? It oscillates up and down, and it has a particular frequency, okay? If I touch the middle, right here in the middle, and pluck it, it goes up an octave. Does anybody play an instrument like a guitar? You know about the harmonics? You can touch it halfway and pluck it, and it doubles the frequency, so it goes up an octave. The same thing here. What you've done by touching it is produced a node, and now you have two lobes, and it oscillates twice as fast. And de Broglie knew about this, and he said, what if the electron around the nucleus is behaving like a standing wave? Okay, so it's not orbiting and getting sucked in or emitting light. It's just oscillating like a standing wave, like a violin string. So he put that into his thesis. Einstein liked it, passed it on to Schrodinger. Schrodinger took a 2-week trip to the mountains, had a good mathematician friend to help him with differential equations, and he solved the hydrogen atom in 2 weeks using this idea. And so this is the fine structure of the hydrogen spectrum across the top. And this is his stick spectrum that he did from his mathematics. It's not a perfect fit, but it's pretty close. So here we see this little 6 lines here. They don't have exactly the same intensity, but they came out at the same frequency. We have this pattern that matches well. We've got this funny little pattern. So all these patterns match really well, and so do their frequencies. So he solved it. He solved the Schrodinger spectrum using quantum mechanics and wave mathematics, so wave mechanics and a quantum idea. So that's where quantum mechanics came to be. And his equation is on his tombstone, so that's pretty cool too. So there it is. And then Dirac extended this wave mechanics idea to multi-electron atoms. So now that we know the energy levels of the electron around the nucleus, we know all the chemistry. But the equations are too complex. So you can see from Dirac in his paper, he says the exact application of these equations is just much too complicated. Some of the equations don't have known calculus solutions. Okay, so we have to approximate them. And so he says it's desirable that approximate methods be used to apply quantum mechanics so that we can get the main features of the chemistry system without too much computation. So I like that idea. And my graduate student and I took that and ran with it, and we produced this spectroscopy theory in one dimension. And so that's her, Victoria, and so we wrote a book together. And so that's the book that's on Blackboard that we're going through, just the first few chapters, okay, to kind of set the framework. So we took this idea of a particle in a box, which is the first problem you do in terms of quantum mechanics in any physical chemistry course. But I had her go through all of the physical chemistry textbooks and find that problem in all of them and see if they went all the way to spectroscopy, like if they went all the way to the simulated spectrum, and none of them did. They always solved for the energies of the particle in a box, and they said, look, it's quantized, but they never connected it to the data that would tell you it was quantized. And so she said, I didn't find it. And I said, I don't believe you. This has got to have been done before. So go look again. So we spent about 3 weeks. She's digging through the literature, trying to find if this was anywhere in science. And it's not, because it's such a simple idea. I think people just didn't even think about it. They'd move on to something else. Okay. And so then when she convinced me that it's not in any of the literature, so then we said, all right, let's write a thesis on it. So she wrote her thesis on it. And then a few years later, I said, I want to turn that into a book. And so actually got approached by AIP Press, American Institute of Physics, and said, we heard, I shipped it out to one book publisher, and they said, we don't write supplemental, or we don't publish supplemental texts. I said, okay. I don't know how behind the scenes it got over to AIP Press, but I got an email that said, hey, we heard you have a book proposal. And so put it in, and it was great. So it's super exciting. So let's think about this idea of this wave nature of an atom. One day my kids and I were going into Target, and I see that big red ball, and I thought, what if that's a proton? How big would the atom be? Right? They get used to this. So I was like, look at this. And so this, I said, I estimated it was a meter wide. So if the proton is a meter diameter, what's the diameter of the atom? Okay. Don't look at your notes. Don't cheat. Okay. What do you think? How big would it be? Big as the parking lot? Bigger? How about Huntsville? The hydrogen atom. Who says Huntsville? It's big as Huntsville. Who says bigger than Huntsville? Okay. How about Texas? The Earth? No. Y'all are pretty good intuition. It's it gets you to Buc-ee's, down to the mall, okay, over to Livingston. It's 71 miles across. Isn't that crazy? That would be the average diameter of the hydrogen atom. So what does this tell you about chemistry? Why is the periodic table, well, first of all, you tell me, how is the periodic table organized? When you did electron configurations, what were you counting? What were you doing? Yeah, and what kind of electrons? We sort of had different types. What? Valence electrons. Yes. Okay. Why is that? Well, because if I'm a hydrogen atom and I'm in Louisiana and I'm coming over to Huntsville, okay, when I get 71 miles away, my electron is starting to talk to the electron of the atom that's sitting in front of target. I'm 71 miles away, but yet I'm already starting to do chemistry. So the nuclei have nothing to do with chemistry. It's all about the valence electrons. And Dirac said, we now know the math of the valence electrons. So we've solved all of the math of chemistry has been solved. But the equations are too complicated for us to do them exactly. So we have to make approximations. But that's what Gaussian is. So when we do Gaussian calculations on the computer, calculate the geometries of molecules and all of that, we're using Dirac's math. to approximate the behavior of chemistry. So it's really cool. And if we need a better result than we can get on our laptop or our PC, then we go to a supercomputer. So that's why our nation has built so many supercomputers. That and AI chatbots, but it's a waste in my opinion. So in summary, we had all these problems with physics that were solved by quantum thinking, okay? It hasn't solved gravity yet. We still haven't folded gravity into this model. So that's really weird. So you think as a scientist, don't be so arrogant. We don't know everything, okay? So we haven't figured out how gravity and quantum fit together, okay? We also haven't solved this idea. This is a quote from Schrodinger. He doesn't like the idea that the electrons jump from one orbital to another seemingly instantaneously. And he says, if all this damn quantum jumping were here to stay, I should be sorry I got involved with the whole thing. Because we can't predict when it's going to happen. That's the whole Schrodinger cat thing. You know, he doesn't know when that nuclear element is going to decay and go from, you know, say an atom is going to split and spit out an alpha particle or something like that. So in order to show the absurdity, he did a thought experiment. He said, we wouldn't say that a cat is both alive and dead at the same time. So how can we say that an atom is both split and not split at the same time? So that it was just an attempt to show how absurd that view is. But that's what the math shows us, that it's an undetermined state until it collapses. And this jumping is here to stay. These Bell inequality experiments, if you want to run down a rabbit hole, start looking at those. This quantum jumping happens faster than the speed of light, which is a no-no. That's our cosmic speed limit. And so how can something happen naturally that goes past the natural speed limit? So we don't know these things, and that's kind of fun. This is the only mention I'm going to do on those, because we're going to get back to the practical stuff of how to interpret spectra and how to understand spectroscopy. But these are some great rabbit holes that you can run down. All right, we'll see you next time.